In this video, we are going to look at the slope of tangent lines to a curve at a specific point, and hopefully use that to develop our definition of what a derivative is. So first, what we're going to do is we're going to use a calculator to graph the function f of x equals 3x minus x squared, which I've already done so for you. What I want to know is how fast the graph is moving at x equals 1, which is just at this location. I want to know what the slope is of that tangent line at x equals 1. Since I can't figure that out right now, what I'm going to do is find the slope between 1 and f of 1 and 1.5 and f of 1.5. So I'm going to create a secant line, which is in the green, and find the slope of that secant line. So f of 1.5 minus f of 1 is going to give me 1.5 minus 1. And after I evaluate that, I get that slope to be 0.5 or half. So what I want to do is I want to keep creating secant lines so I get closer and closer to that tangent line that I have on this curve. So what I'm going to do is my points, I'm going to change from being 1.5 to just be 1.1, 1.01, and 1.001, so that each time I'm getting closer and closer to that actual tangent line where x equals 1. So it's similar to what we used to do with our limits and creating our tables. Okay. So first, if I want to do C at f of 1.1 minus f of 1, where the value that I want to find, 1.1 minus 1, I find that slope of that line, and I get 0.9. Okay. What I'm going to do, I'm going to get even closer to 1 than I can. So if I want to do f of 1.01 minus f of 1, again, I'm finding the slope of that line, and this time I get 0.99. I want to get even closer to 1, as closest to 1 as I possibly can get. So I'm going to do f of 1.001 minus just f of 1, 1.001 minus 1, and I get 0.999. So each time I'm picking specific x values, so I'm getting closer and closer to the x value that I am concerned with, that I actually want to find the slope of that line. So based off of these calculations, as I keep approaching and getting closer and closer to 1, what do you estimate that the slope of my tangent line at x equals 1, and I'll draw it in again, is going to be? So a good estimation would be that the slope of my tangent line at x equals 1 is also going to be 1. Because I'm getting closer and closer and closer. And that is just based off of my previous slides, where each time I picked an x value that was closer and closer to that value of 1. So what we're going to do now is keep working with that same function, 3x minus x squared. But what I want to do is I kind of want to do it in terms of, I don't necessarily pick the x value, I'm just choosing an arbitrary x situation where how far as I am from that one value. So what I'm going to do is this time I want to find the average rate of change, which again, my average rate of change is just those slopes of those secant lines. And this time I want to find it between 1 and f of 1, and 1 plus delta x and f of 1 plus delta x. And where this time my delta x is going to be that change in my x between my two x values. So I'm not actually specifying what my second x value is. All right, so got to work through some algebra here. So if I want to do f of 1 plus delta x minus f of 1 all over 1 plus delta x minus 1. What I need to do in the first one is I need to plug 1 plus delta x in wherever I see an x. So I get 3 times 1 plus delta x minus 1 plus delta x squared. And then minus, I need to plug a 1 in. So I get 3 times 1 minus 1 squared. And all of that is going to end up just being over delta x because the 1's are going to cancel. All right, now I need to simplify my numerator. So I end up getting 3 plus 3 delta x. Now I have to FOIL the 1 plus delta x out and also distribute that negative sign. So I get minus 1 minus 2 delta x minus delta x squared. And then that's going to be just a minus 2 all over my delta x. Then combine some like terms on the numerator. So I end up getting 3 minus 1 minus 2, that all cancels out. So I'm left with 1 delta x minus delta x squared all over delta x. I can divide through by a delta x, so I just get 1 minus delta x. Okay, so what that is going to equal is that's actually my a of my delta x. So what I'm saying is my delta x gets closer and closer and closer to 1. That's what I can approximate to be the slope of that line. So for example, if I go back and think about 1a, if you're letting your delta x equals 0.5, because remember I wanted to find f of 1.5, and 1.5 is a half unit away from 1, then if I plug this in, then I end up getting that my a of 0.5 is 1 minus 0.5, so my slope was a half, which is what I calculated before. If I go back to 1b, this time I let my delta x be 0.1, because remember I wanted to find f of 1.1, so that's only 0.1 units away. If I plug that in, I get a of 0.1, which is 1 minus 0.1, which is 0.9, which was the slope of that secant line. And then also, if I chose 1c, that was 0.01, because I want to find f of 1.01. Same thing's going to happen, a of 0.01, 1 minus 0.01, which is 0.99. So this is another way that I can actually find the slope for any pair of any secant lines as I approach that specific x value, which in this case was a value of 1. Okay, so this is kind of answering our next question. What happens to the secant lines between the points 1 and f of 1 and 1 plus delta x and f of 1 plus delta x as delta x gets smaller and smaller and smaller? Well, as your delta x is getting smaller, then the slopes of the secant line are approaching one value. And more specifically, that one value that they are approaching, this is actually the slope of the tangent line at x equals 1. So that value that they are approaching is the slope of that tangent line at x equals 1. So what I want to do now is I want to take the limit as delta x approaches 0 of my a of delta x. So if you remember, my a of delta x is really just 1 minus delta x. So what I can do now is as I take the limit, I can use direct substitution, so I just get 1. Well, 1 is the slope of that tangent line. So by doing the limit, it's actually telling me what the slope of that tangent line at x equals 1 is. Another way we're going to think about it, it's the slope of the tangent line, but it's also my instantaneous rate of change. It differs from average rate of change because average rate of change involves 2 pair of points, and I'm finding the average between them. Whereas instantaneous is I want to look at 1 point on that curve and know exactly how fast something is moving at that specific x value. So in this case, that at x equals 1, I am moving at an instantaneous rate of change of 1. All right, so what we're going to do now is keep working with the same function, but instead of always evaluating it at 1, I want to come up with a formula so that I can evaluate it at any x value that I want. So I can find the tangent of any x value, the tangent line, the slope of any tangent line, excuse me, at any x value. All right, so what I'm going to do now is I'm going to ultimately do the same thing. I'm going to use a similar method, but I want to find the general formula for finding the slope of any tangent line. So this time, I'm going to use the point x and f of x instead of 1 and f of 1. So that's where it's going to change a little bit. All right, but I still want to take that limit. So here's what I'm going to do. I'm going to take the limit as delta x approaches 0. And I want to find the slope or the difference between these. So it's going to be f of x plus delta x minus f of x all over x plus delta x minus x. So that's still my slope formula, but this time I'm doing it in terms of just x's. So then when I go to plug some stuff in, I end up getting, I'm going to do 3 times x plus delta x minus x plus delta x squared minus 3x minus x squared, excuse me for that, all over, it's just all over going to be all over delta x because the x's are going to cancel out. And that's going to equal the limit as delta x approaches 0. Now I need to FOIL out and distribute that top. So I get 3x plus 3 delta x minus x squared minus 2x delta x minus x squared minus 3x plus x squared all over delta x. Make sure you know how I FOILed all that out. Then I can combine some like terms, so I still have the limit because I did not evaluate yet. And I'm left with 3 delta x minus 2x delta x minus delta x squared all over delta x. Now I can actually divide through by a delta x. So I get the limit as delta x goes to 0 of 3 minus 2x minus delta x. Now I can actually use direct substitution, and I do that, so then I end up getting 3 minus 2x. And what this gives me is this one is an equation to find the slope of any tangent line at any x value. So if I wanted to choose a different x value than, let's say, 1, I wanted to see what's happening maybe at 2. So I wanted to find the slope of a tangent line at x equals 2. Instead of going back through all the algebra and finding, so instead of doing what, this 2 plus delta x minus f of 2 all over 2 plus delta x minus 2, instead of going through all that algebra, I can actually just do 3 minus 2 times 2, which gives me a negative 1. So the slope, or the instantaneous rate of change, at x equals 2 is negative 1. That's how fast that curve is moving. So all of this, what this means is this is actually the derivative function. So what we did by finding our slope function in this previous example, by just doing it in terms of x's and delta x's, we actually found our derivative function. Derivatives are going to be used to find the slopes of the tangent lines at a single point. Okay? That slope of my tangent line, remember, is also going to be referred to as your instantaneous rate of change. So that's going to be known as my derivative. A function that has a derivative at that specific point is said to be differentiable at that point, and we'll talk more about that. So in this video, hopefully now, we have a good definition of what our derivative is, and this is what it is. So basically, I can pick any x value that I want on my curve, and as long as I'm choosing a delta x and I'm getting closer and closer to that x value, that if I set this definition up, I'm ultimately finding what that slope is at that specific x value. I'm finding the instantaneous rate of change at that x value.